Hello, friends. Now we're going to talk about curvature of a plane curve. So we're starting to study how a curve turns or how a curve bends. And we're going to begin by looking in a coordinate XY plane. And then as we understand in 2D, we'll move forward and then talk about them in space. So we have a curve here. And as the particle moves along the smooth curve, we have all these tangent vectors, and these are t, or the tangent unit vector. So they're of length 1. They're really just giving us direction. And so we see that the slope of these tangent vectors, in a sense, are changing as the curve, our curve C, that blue line, bends in our Cartesian plane. So just to rephrase what's going on here, as this point P, starting at some initial point P naught, as P moves along the surface of this curve, C, it's an increasing arc length of the curve. That unit tangent vector, T, is turning. This is what we call the curvature, right? The rate at which T, my tangent unit vector, turns per unit length along the curve. And we use the symbol kappa to illustrate this. So I know I've been writing cursive lowercase k's. When we talk about curvature, we represent it with a fancy K. Your books kind of looks like this, but I will draw my kappas like that. So we're going to talk about kappa. So if T is the tangent unit vector on some smooth curve C, the curvature, which we call kappa, is the magnitude of the derivative of that tangent unit vector with respect to S. So in case we haven't been up to date on all of these videos, let's recall a few things considering where these values are coming from. So R of T, this vector R of T, that's my position vector. And we know that if we take the derivative of my position vector, that gives me my velocity vector. We know that the tangent unit vector T is equal to the velocity vector divided by its magnitude. Or we could say R prime of T divided by the magnitude of R prime of T. Right? And so what we're doing when we start thinking about curvature is we're looking at indicating the direction of the curve, right? The curvature is telling us, at some point, how rapidly is the direction of my unit tangent vector, which a unit vector is only telling us direction. It has magnitude of 1. So just to kind of visualize this and kind of draw it with you, if I have my XY plane and I have some curve that maybe, I don't know, goes all over the place like this. If we start looking at the tangent unit vectors near this max or this min, right? And here we're looking at a max, but if we think about all of these as being different tangent unit vectors, what we notice is up here at this peak, the direction is rapidly changing, right? So the direction has a larger change. In a short period, we went from positive to negative. But then we may also have situations, like if I were to look at a point right here, and we think about the direction, these aren't very good tangents, but you kind of get the idea. They're all kind of pointing in the same direction. So this has a slow change. So there's not a lot of curvature here, and there's a great deal more curvature happening at that maximum. So in layman's terms, my kappa curvature is telling us how rapidly my unit vector t, my tangent unit vector, is changing. All right, remember t is a unit vector of constant length. The kappa curvature, this is only going to be affected by a change in direction. And so let's look at how we get this formula. So I said that kappa equals the magnitude of dt with respect to s. And if we apply the chain rule, we can break this into pieces. So that would be the same as writing dt dt times dt ds. Now, we can separate this, and I can say, well, this is the magnitude of dt dt. And then if I think about multiplying by dt ds, remember that multiplication is the same as dividing by that reciprocal. So ds dt, the derivative of position with respect to time. We still have magnitude bars around that. While the derivative of position with respect to time, that's equal to the magnitude of velocity. So what we've done here is we have the formula for calculating curvature. So as long as we have r of t being smooth, smooth is important for it to be differentiable, but if our position vector is a smooth curve, then the curvature is defined by this scalar function k, which is 1 over the magnitude of the velocity times the derivative of the tangent unit vector, where the tangent unit vector is defined as the velocity vector divided by its magnitude. So now let's do an example. In this example, we're going to find the curvature of the vector r. This vector is representing a circle in parametrized form. The circle has a radius a, so a cosine t plus a sine t. If you thought about that in polar coordinates, r sine theta plus r cosine theta, that would give you a parametric circle. We want to find that curvature. Curvature is defined as kappa equals 1 over the magnitude of the velocity times the derivative, and that should really only be over the t, the derivative of the tangent unit vector's magnitude with respect to t. All right, so we need velocity and we need the tangent unit vector. So first things first, we'll find v. The derivative of a cosine t would be negative a sine t. That would be times I, plus the derivative of a sine t would be a cosine t j. All right, so we need the magnitude as well for this. My magnitude, the magnitude of v, is the square root negative a sine t squared plus a cosine t squared, which is the square root of a squared, sine squared t plus a squared cosine squared t. If I factor out my a squareds, I've got sine squared plus cosine squared, which is 1. So this is equal to the square root of a squared, or just a. So my tangent unit vector, t, that is v divided by a. So v is a sine of t I plus a cosine of t j, and we divide that by its magnitude, which is a. So this simplifies. I have t, my tangent unit vector, equals negative sine of t I plus cosine of t j. All right, last thing we need before we can calculate curvature is we need the magnitude of the derivative of the tangent vector with respect to t. So we need the magnitude of, first we'll find the derivative in here. So the derivative of negative sine is negative cosine t I, plus the derivative of cosine is negative sine t j. And the magnitude that is, we're going to get cosine squared t plus sine squared t, the sum of the squares of the components, square rooted. So our radicand, what we have under the radical, is 1 by our Pythagorean trig identity. So the magnitude of the derivative of the tangent unit vector with respect to t is 1. What we can say here, hence, for all values of the parameter, which is t, the curvature so that curvature, kappa, we have 1 over the magnitude of my velocity vector v, which was that light blue part there. We got a, times the magnitude of the derivative of the tangent unit vector, which we get is 1. So we end up with 1 over a, or rather 1 over the radius, because this was a circle of radius a. So this formula should make sense, or it should work. But we have a better, more convenient formula coming up, right? So this is kind of like our intermediate step to our super shortcut formula, or a formula that's a little easier, less labor intensive, because we had to calculate a lot of things in order to find this curvature.